Welcome to General Chemistry Mini Lecture Series, Lecture 37, Electron Configuration and the Periodic Table. In this slide, we divide the periodic table into several blocks. We have the S block, the first two columns, then the last 6 columns, P block, the one in between, that's D block for transition metals. And then here, that's the F block. S blocks means the electrons occupy this block, they are S electrons. And means the number of the period as well as the principal quantum number. So for group 1A, the electron configuration should be always S1. Group 2A should be always S2, including helium here. For P blocks, we start from P1, P2, all the way to P6. Please note, the length of each block is the maximum number of electrons the subshell can hold. So for S block, you see, only 2 columns. Therefore, the maximum number of electrons for S block is 2. Why? Because there is only one S orbital. According to Pauli exclusion principle, maximum only 2 electrons can be accommodated in S orbital. And for P, there are 3 P orbitals. Each orbital can accommodate 2 electrons. Therefore, the maximum number of electrons in the P block is 6. For D block, a total of 10, maximum of 10 electrons can be accommodated, and for F block, a maximum of 40. The period number, like n minus 1 or n minus 2, so that corresponds to the principal energy level of the valence electrons. We already know for group 1A, the electron configuration should be S1. Therefore, the general form for electron configuration for everything in this family, that should be NS1. For hydrogen here, N equals 1, or that's the first period, that should be 1S1. For lithium, 2S1. Sodium, 3S1. Potassium, 4S1. And rubidium, 5S1. And now if we concentrate on period 3, sodium 3S1, magnesium 3S2, and here that should be aluminum 3S2, 3P1, silicon 3S2, 3P2, phosphorus 3S2, 3P3, sulfur 3S2, 3P4. See, that's the P4 column, then P5, then P6. Now let's take a look at the transition metals, the D block. Please note, in the D block, the principal quantum number, you have to use n minus 1. So therefore, for titanium, the electron configuration for the valence electron, for the valence shell, should be 4s2 because the S block is already fully filled. And then there are 2 D electrons. That's why it should be D2, but it's not 4s2, 4d2. This is a 4 minus 1, 3d2. That's how you use this n minus 1 for the D block. And when you write the electron for configuration for the elements in the F block, okay, you need to use n minus 2 for the transition metal in the fourth period. The valence electron configuration again is 4s2, 3d2, 5s2, 4d2, n minus 1. You see 5 minus 1 equals 4. 6s2, 5d2. Again, for the D electrons, you have to use n minus 1. Now, when writing the electron configuration for atoms that have 4 d electrons and 9 d electrons, you need to be careful. In this case, you should not use D4, you should use D5. Move one of the s electrons to the D block. And for the one with 9 d electrons, again, you need to do the same. Move one of the s electrons to make D10. This is a D5 halfly filled, D10 fully filled. Because of symmetry and energy exchange, the halfly filled and fully filled orbitals have much lower energy. Therefore, the system should be much more stable. Just a quick note here, you see, if you are asked to write electron configuration of an atom, you just grab a copy of periodic table, find out its location, then you can easily get the job done. For example, if you want to write the electron configuration for strontium, you just find out the location of strontium, and this is in period 5. Therefore, the valence electron configuration should be 5s, and its group is 2a, so therefore should be s2. If you want to write down the condensed electron configuration for strontium, you will use the noble gas from the previous period. In this case, it's krypton, and therefore that should be krypton, and then write down the valence shell electron configuration. That's it. That's easily done. Use the same way, you should be able to write down the electron configuration for any atoms you can find in a periodic table. You just need to find out the location, then follow those rules I just showed to you. We already learned this in the past. For group 1a elements, they always form 1+ cations. Group 2a elements always form 2+ cations. Group 7a, normally -1 anions. Group 6a, typically 2- anions. After forming ions, whether cation or anion, so those ions will result in an electron configuration that is the same as the nearest noble gas. So in group 8a. You already know anions are formed when atoms gain electrons. How many electrons should they gain? They will gain enough electrons to have 8 electrons. What is special with 8 electrons? The octet rule. Let's look at sulfur though, okay? Group 6a, it has 6 valence electrons. It needs to gain 2 more, you see? So here, that's 6. valence electrons, 2 plus 4, that's 6, and gain 2 more, that's 8 electrons. And now sulfide has an electron configuration as the same as argon. It's nearest noble gas. And we know argon is very inert, it's very stable. Therefore, we can say sulfide actually is more stable than sulfur. The anion is more stable than the atom. Cations are formed when an atom loses all of its valence electrons. Calcium has 2 valence electrons, group 2A, 2 valence electrons. After losing that 2 valence electrons, there are no valence electrons anymore. Everything is fully filled, and this electron configuration is the same as argon's, which the nearest noble gas for calcium. Calcium 2 plus cation is more stable than calcium atom because of the inert gas electron configuration the ion has. Let's see one more example for main group elements. Aluminum atom, electron configuration. The valence electron, 3s2, 3p1, losing all of the 3 valence electrons. This electron configuration becomes neon's electron configuration because the neon has 10 electrons, and now Al3 plus has 10 electrons. For transition metals, almost all of the transition metals will form 2 plus ions. That's because they will lose the 2 s valence electron. That's why it's very often for transition metals you will see 2 plus ion. Iron, this is the iron atom's electron configuration. Iron 2 plus, you see the 4s2, those 2 electrons, they are gone. Iron 3 plus, after losing the 2 4s electrons, one of the 3d electrons has to be removed. That's why iron 3 plus ion ended up with 5d electrons. 2 of the 4s electrons are lost, and 1 of the d electrons is also lost. That's why you have the electron configuration for iron 3 plus like this. This is the electron configuration for copper atom. You may notice this is 4s1, 3d10, and this is the correct electron configuration for copper atom. If you write 4s2, 3d9, the number of electrons are the same, but that is the incorrect electron configuration for copper atom. Because in that electron configuration, the 3d orbitals are not fully filled. But here, the 3d orbitals are fully filled, so it's more stable. And now you have the copper 1 ion electron configuration, 3, still 10 3d electrons. Copper 2 plus, however, there are no s electrons available. The system has to lose 1 of the d electrons. Isoelectronic series is a group of atoms or ions that have the same number of electrons, like what you see here. So you have atom, you have anions, you have cations. First, let's look at the atomic number for those elements. So the atomic number also means the number of electrons in those atoms. So for sulfur atom, 16 electrons, but gaining 2 electrons becomes s2 minus. The number of electrons for s2 minus is 18. Chlorine atom has 17 electrons, gaining 1 electron, 18. Argon atom has 18 electrons. Argon atom here should have still 18 electrons. Potassium has 19 electrons. Potassium atom has 19 electrons. Losing 1 electron becomes K plus 1, then 18 electrons. Calcium, 20 electrons, losing 2 becomes calcium 2 plus, then the cation here has 18 electrons. So now you see all of those 5 ions and atom, they have the same number of electrons. That's why we call this kind of series isoelectronic. That's it for lecture 37. If this video is helpful, please subscribe to this channel. You are also welcome to recommend those videos to your friends who are also taking chemistry. I will see you guys in lecture 38, effective nuclear charge and magnetic properties.